Hello everyone. Today we're going to talk about the topic, the evaluation of dyes in the dye sensitized solar cells. We all know that the DSSC is a photovoltaic technology which converts the sunlight into electricity using a photosensitive dye. Choosing this photosensitive dyes is a very critical and a crucial process because it directly depends on the efficiency and performance of your solar cells. So without any further ado, let's briefly discuss about the evaluation of dyes in this video. So the evaluation of dye has key factors such as the number of functional groups present in the dye and the distance between the anchoring hydrogen to the LUMO electron density and the trap states and the stroke shifts value, and also the electron injection efficiency from the dye to the MOS. So here we can see two ruthenium based dyes in which the first dye has 4 functional groups and the second one has 2 functional groups. So basically the dye with more functional groups will generate more short circuit current than the other one, because the excited state electrons could be injected into the photoelectrode in a faster rate and in higher number. Basically, this functional groups acts as a syringe to inject the electrons into the photoelectrode. So we have seen that the more the amount of functional group present in the dye, the more will be the efficiency. But what if you have more amount of dyes which are having the same amount of functional group? How will you select the most efficient dye out of them? So here comes the role of the anchoring hydrogen. Anchoring hydrogen is the one which is present in your functional group. In this case, we are having the COOH. The H is the anchoring hydrogen. We have to see the distance between the anchoring hydrogen to the LUMO electron density. The shorter the distance between the anchoring hydrogen to the LUMO electron density, the more efficient the electron transfer from the LUMO to the conduction band of your semiconductor. So the third aspect we're going to discuss is about the trap states. We are going to use an instrument named photoluminescence spectrometer, in which we are subjecting a bare dye to a photon radiation. So once the photon is injected into the dye, the electrons present in the dye will be get excited to the LUMO level. As it is a bare dye which is not attached to any semiconductor layer, after some time the electrons present in the LUMO will be combining with the hole in the HOMO. So this electron hole recombination is a radiative process, and we'll be seeing a peak in the PL spectrometer, in which we can compare if the photon in value is equal to photon out, the dye does not contain any trap states. But if the photon in value is greater than the photon out, we can absolutely say that there are trap states present in the dye. So in this slide, we can see that the photon in value is matching with the photon out value, which means the dye does not contain any trap states. We can see both the photon in and photon out are coinciding in the same graph, meaning that it has no trap states. So in the second case, we are saying the photon in is greater than photon out, which basically means that there are trap states in the dye. So we are going to use two instruments, which is the UV visible and the PL spectrometer. The UV visible will provide you the absorbance value, and the PL intensity will be provided by the spectrometer. So basically, the energy of the absorbed photon is greater than the energy of the emitted photon, which basically means the emitted photons have longer wavelength than the absorbed ones. So on subtracting the values like x2 minus x1 will provide you the stroke shift value. So the lower the stroke shift value for a dye, the higher will be the efficiency, because the gap is arising because of the trap states. So the lower the trap states, the more the efficiency. So the final aspect in the evaluation of dye is that the electron injection efficiency from the dye to the MOS. So basically, we are comparing two things. The first one is the bare dye, and the second one is the dye attached with semiconductor layer. The bare dye, when we irradiate it with photon, the electrons get excited to the LUMO level, and it does not have any pathway to inject its electrons. So after some time, it will recombine with the hole in the lower layer, and this process is absolutely radiative, and we'll be seeing a broader peak in the PL spectrometer. Whereas in the second case, we are having the TiO2 layer or any semiconductor layer. So the electrons from the LUMO level will be injected into the conductance band of the semiconductor, which will give you a quenched peak in the PL spectrometer, indicating that the electron is injected. So the more the quenching of the PL intensity curve indicates that the more efficiently the electrons has been injected from the LUMO layer to the conductance band of the semiconductor layer. So we can see that even though we are having a semiconductor layer, not all the excited electrons will be transferred into the semiconductor layer. Some of the electrons will be transferred, will be recombining with the hole. So we'll be having only 70 to 75% efficiency rather than the 100% efficiency. Even though the energy alignment is in the right way, the conductance band is lower in energy than the LUMO level. Not all the excited electrons will be injected into the conductance band. Some of them will still recombine, which will lowering the efficiency. So basically, this is the evaluation of dyes. So all the factors we have discussed in the evaluation of dyes directly influence the factors such as light absorption, charge transfer, and the recombination. So by selecting a dye that excels in these areas, we can maximize the energy conversion efficiency of our cells, as well as it will increase the overall performance and stability of the solar cells. So now we'll discuss about how artificial intelligence and machine learning are revolutionizing the efficiency prediction for the dyes we are using in the DSSCs. Traditionally, the dye evaluation for DSSC cells relied heavily on time-consuming experimental procedures requiring the analysis of multiple parameters like functional groups, LUMO electron density, and the trap states, which we have seen in this video. But while effective these methods are, they can be costly and very slow. So now imagine being able to predict the efficiency of a dye without going through this endless trial and error. This is where AI and ML come into play. By training models on existing datasets, we can stimulate and predict outcomes with precision, accelerating the development process. So without any further ado, let's talk about the AI and ML in the prediction of dyes in the DSSCs. So we begin by collecting data from conventional sources and then move to data pre-processing, ensuring that there are no errors in the collected data, which will potentially lead the model to predict inaccurately. In the model training phase, the model is not only trained, but also it predicts dye structure. Next, during the optimization process, we have to synthesize the predicted dyes in the lab and check its efficiency using the traditional methods. So if any flaws arise in the predictions, the model should be refined accordingly. This refinement enters a feedback loop, and through continuous iterations of trial and error, we ensure that the AI remains efficient in predicting dyes. So that's it about the AI and ML dye efficiency. In the iterative process of AI and ML in the dye efficiency optimization, the first step is the data collection, and then we have to pre-process the collected data to ensure that there are correct values, and then we have to feed the model with the collected data, which is the model training. In the training phase, the model will predict the dye structure which have most efficient dye. So we have to synthesize the predicted dye, and then we have to test its efficiency conventionally, and then we'll be having two results, which is the AI predicted one and the one we have done conventionally. We have to match these, we have to compare these two results. Of course, there will be flaws in the results at the very first stage of the AI prediction. We have to feedback the AI with the real world data, which will ensure the AI to get refined itself. This is the model refinement. This is in continuous process of trial and error of AI to get the most efficient dye. This is an iterative process, and it have to be repeated again and again to ensure the efficiency of the AI to predict the most efficient dye. So what are the advantages of using AI and ML to predict the most efficient dyes? First thing, it is time efficient and it will recognize the pattern more easily. And in the optimization process, it will predict the dye, it will predict the best performing dye combination using the data we have provided in them, and it will reduce the cost, because if we perform the experiments conventionally to find the LUMO electron density and the number of functional group present in it and efficiency of electron injection, it will include various instruments like spectrometer, etc., which will increase the cost of the experiment. So these are the advantages of using AI and ML to predict the efficiency of dyes. Thank you.